mention that this is the center of the campus, and the fountain here is from the Yukon Pacific exhibition around 2019 or so, 1919, around that time. So I again want to thank Vaibhav and the faculty in Michigan State for inviting me for this talk. There's a little bit of theory in here, which I might not go through in detail, but that's all in the Automatica published in 2020, February. Okay, so let me give you a brief intro. Of course, sometimes people don't know where University of Washington is, because there are many Washingtons, So we're talking about the state, which is in the northwest corner of the United States. And if you ask me or anybody what's Seattle famous for, mostly rain and of course coffee too. But rain does make Seattle very beautiful. We have the Mount Rainier and the Olympic National Park. The center of the campus is spectacular. Actually, this picture is from a few years ago, but I just went by the campus this time of the year. The trees look spectacular. And we have the Puget Sound, which is very important for the economy of the region. And I also want to welcome you to Seattle. We have the AIM 2023 is going to be in Seattle. Most welcome to submit papers if you want to have invited sessions or workshops, or if you want to participate in the OpCom or anything like that, do let me know. And if you think about the other famous things in Seattle, so the Boeing company started in Seattle, partially because of the water, the rainfall. We had the big hydro dam and the power was cheap, and so production was cheaper, and that started out here. Microsoft, of course, came in a little bit later. Starbucks is a popular Seattle thing. Apple's UPS is a Seattle company, started out a long time ago with bicycles. Costco is a Seattle company. And then the PACCAR, the trucking company, is also nearby to the north of the university. And then, of course, now the big gigantic company in Seattle is Amazon, and it has a lot of buildings in the downtown area. And the space industry is also starting up in Seattle with the Blue Origin. So it's a lot of industries in the region. And the university has been trying to connect up with these companies because these are famous companies, and then we're trying to put together centers and so on. And of course, the University of Washington, which was established in 1861. So we have about 48,000 students. I think one of the things we are kind of somewhat proud is this innovative public university ranking we got, partially because we have a very good group that allows innovators to work with investors and tries to pair them up, and the tech transfer office is fantastic. And then this, of course, is the cherry blossoms in Seattle. And so part of that effort of looking at the local industries and connecting up was trying to see if we can leverage our local industry. And this Boeing Advanced Research Center is an outgrowth of that desire to work with the local industry. So it started out in 2014, and the major challenge was putting together all the IP packages to bring together faculty and researchers from the industry together in a single space. So we have some full-time Boeing employees working there, and they work with the students and faculty. So we have about 8 to 10 projects everywhere, mostly centered around machine learning and database methods for many of the robotics and manufacturing applications. There's a lot of interest because a lot of work is done by humans. There's a lot of interest in trying to increase the number of robots in aerospace, because mainly out of safety issues and ergonomics issues, and composites obviously is a very important topic. The second thing that's been going on for a while, and recently my efforts have been trying to put together this composite center. As you might know, putting a center together requires space, money, equipment, people. So it's a slow and long process. We have been talking to a whole bunch of industries. We have a few initial sponsors. We got a keystone project from the state along with Boeing to bring in this huge fiber placement machine. And we are in the process of making concrete, and all that stuff is what's going on these days in my life. But the research topics are essentially going to be on database methods and approaches to try and make composites manufacturing if possible, a little bit faster would be nice, but still maintaining quality. So that's the essential challenge there. So, we always wonder why should the universities work with industries, right? So it's definitely is a excellent way to get application-based learning at all levels, from bachelor's to PhD. And I think, the students learn by doing, they see the applications and they tend to be very motivated, especially I've found students, the bachelor students, master students, and even the PhDs, the having a Boeing person next to them in the same lab and being able to ask questions seems to be very exciting for them. And so definitely there's impact for whatever research you do in this collaborative effort. But the other important thing is that, these problems are really hard. Industry solves them to a certain point, but there's a rich set of problems that you can generate from that leads to interesting academic research as well. So before delving into the topic of network controls today, I want to talk about, what my basic things I do. And so inside the wing, which is a lot of manufacturing goes on, to do anything inside, including maintenance or inspection, people are suiting up to go inside. And then, if you have already, if the aircraft is flying, then there's a fuel tank as well. And so you're wearing masks and all kinds of gears when you're going inside. It's a pretty nasty environment to work inside that. And so, there are several topics that come up, and I'll just give you a brief intro to these three topic areas that we work on. One is on human in the loop learning, and so you're trying to do some task with a machine in the middle, and so this was work done by Rahul, and he graduated recently. So the idea here is that there's a human operator, and there's a machine the operator is trying to control, pretty much like a teleoperation task, and the system as an output. And so what the human is seeing is, human knows what you're trying to do, and you have a system output, and the human is looking at the difference and sending commands to the system. Okay? And of course, the major problem is that, what is the human trying to do? This YD is unknown to the machine. So let's assume that the machine is really good, like a robot, feedback controllers are really great, and so the transfer function is 1. Even then, the machine is not able to track the trajectory exactly because the machine only knows what the human is trying to do, not what the human actually wanted. So the human output is not exactly the same as the desired intended goal. So that becomes a problem in this kind of scenarios. Now, of course, when the human is really good, they eventually figure out how to adjust these inputs to the machine so that you get the desired trajectory you want. And they can even learn the control system dynamics over time. The difficulty happens, and so our interest was, if you're doing a medical robotics problem, you can train the doctors for a long time, and they're very expensive. But on the other hand, in a manufacturing setting, you have novice operators. There's a substantial turnaround that happens, and so the human may be a novice. And so our basic idea was to say, okay, if you could model the human dynamics, then you could look at the input that the human is applying to the machine and the desired, the actual output of the system, and then hopefully infer what the intended goal was. Okay, and then we are trying to use that for improving control tasks. And so that was the basic idea here is, you take the model of the human operator and then in blue here in the top left corner. And even with multiple iterations, it's not easy for the human to correct everything, especially even if you're going about 1 hertz, a couple of hertz, it's very difficult for the human to track a trajectory if you don't know the trajectories ahead of time. And so you get substantial error in the human. And then of course, you do the shared control and eventually the machine is able to understand what the human was trying to do and get good correction of that thing. And this basically shows about, the overall how the intent is observed over time. And there's a couple of publications inside here. And the main idea was, modeling of the human and trying to correct for it. The second set of problems is when the human and machine are doing something together. So it's not like the human is trying to drive the machine, uh, feedback loop. But if you like, if there's a prosthesis example, Jonathan that worked on it, and he's just graduated, he's actually going to join UC Riverside this fall. And in this work, you have a prosthesis and a human. So both the human puts a load on the other on that leg, and the prosthesis itself can put a load as well. So now you have two things trying to control the same output in some sense. And then maybe both of you are novices. Human is trying to figure out things, and the machine is trying to figure out things. And then, of course, that you're not sure whether you'll remain stable. So that led to this more generalized problem here, saying that, okay, you may have a system with a bunch of agents putting inputs, and the sum of all that is the output. And then, of course, you could do an iterative update law for each of them. So you can look at the total output, and you can look at your own, actually, you don't know your exact output. You can actually look at the actual final Y. And they're hoping that, by iterative methods, you can do some corrections for this. And so the update law for each agent is, the previous input plus the error between the desired trajectory and the total trajectory at the end of the kth iteration. And if, let's say, you have a model of your own dynamics, you invert that with a gain. Okay. And so this is a standard iterative control law, but the key difference here is that there's two, you think of this iterative gain as two parts. One part is if you're working by yourself, no other agents, and then you have some gain that allows you convergence. And then this is a second weight that scales it down. So this rho ik is a scaling that goes to your original weight. That has to be less than 1, and it's a partition of unity. So basically, you have summation of all these things are 1. And the main result we got from this was saying that, okay, as long as the partition adds up to 1, and it's less than 1 for each one, we can show that this network of this collaborative effort will still converge if your original iterations converge for the individual system. Okay, so if as a single one you could converge, then the sum of all those will also converge if you have partitioned it correctly. And any partition works, actually. The third problem we are looking at is confined space problems. And we were looking at some cleaning operations, where you have whole cleaning. Now, if this is a small robot that you would like to put inside the tail section of the wing, where people go in manually trying to do cleaning operations, essentially you're cleaning the hole before you're doing other operations on it. And so here's a person trying to demonstrate that, and you try to understand what is the, try to have a dynamic notion of what the task is supposed to be. Then you try to learn that task. And then once you learn it, of course, the robot can always mimic that task. And the idea is that if you now have multiple holes, then initial positioning is always difficult with this system. So you start doing the initial operation, then the robot figures out where you are, and then it takes over and does the rest of it. So that's that actually project went well. One of the problems we of course find is that with these kind of actuators, if you go at very high speeds, they're not very precise. And so now we are trying to see if we can improve the precision as well, with this kind of learning tasks. And we have a small NSF brand that we're working on. So those were the background work on the different problems we look at, inspired partially by the Boeing Center. Now I want to talk about the cohesive networks for today's topic. And there's a lot of research and so on. This is some videos, from birds to fishes swimming around the oceans. Those were inspired a lot of research. There's a substantial number of effort in this area already. It's been going on since the 90s. And many in our community work on this topic, Xiaobo and everybody else here, I'm sure, knows this extremely well and they worked on the topic. So the question is why, right? What's the interest in this? And so I got interested in it from hearing about this paper in one of the controls conferences. They were talking about, there was a group of people who actually collected data from birds flying in a flock. And then you take the data and from that try to see, what kind of behavior can you observe. And then you try to see whether our current models match that. Okay. And so essentially they collect the data. This is from their paper. It's, they have the videos of that discretization, and you can download these things. Um, but the interesting thing is that, they basically are saying that, our existing models are pretty much diffusion based, okay? And so in that case, the response should decay as it propagates around the swarm. And what they found is that doesn't quite happen. And so we'll talk about that a little bit. And basically what they're finding is that the swarm's motion is more cohesive than what the model should predict. Okay, so that's the basic thing. So what does cohesion mean? Okay, just to give an idea. So in this case, in their case, what they're saying is that they can find the acceleration, radial acceleration of the birds. And the red ones are the ones which are closest to the very first birds who start the maneuver, and then other birds follow up. And so the green ones are a little bit further away from the leader bird, and the next one, the blue ones, are even further away from the leader bird. And so in an ideal case, all these accelerations will look exactly the same, okay? And all the magnitudes will be exactly the same. There's not much difference between them. That will be cohesive. In that case, everybody is making parallel turns. Okay, their trajectories are parallel to each other, and the formation remains the same. So that would be the ideal case for cohesive behavior. Now, if you might know, if you look at the orientation dynamics in a network system, current theories basically try to ensure that at the end of the transition, the orientation is the same. Okay, but not during the transition. So cohesiveness here requires the things to remain similar during the transition. Okay, so this motivates our current effort. Why doesn't the models match? What we like to change in the model, and of course, there's lots of engineering applications if you can try to understand what's going on in here. So let me briefly describe the swarm model. Now, this is the simplest model that you can think about. Obviously, this is starting from the 1990s, roughly. A bunch of papers that then motivated, controls people also to pick up similar models. So the idea here is that, we'll do a planar dynamics here. We'll assume that, each agent has a position x, y, and yi. The speed is assumed to be a constant here. And essentially what is changing is the orientation in the plane, okay? So the orientation is this I. And so if you look at a discretization, at the so these are the time intervals tk, k times the sampling time. So what you're doing is your state x is changing from the previous one to the next one by velocity times cosine of the angle. And for the yi, it's the velocity times sine angle. So you're taking the orientation, splitting your velocity into the x and y coordinates, updating it by delta t. So it's a really simple model. And changes happen because there's orientation changes, okay? And the key point is that this orientation information needs to be propagated through the network. So here's an example. It's a randomized set of initial conditions, and they're all oriented in one direction, and they're going to try and change orientation. There's a single thing somewhere in the middle here. That's the main one, and that initiates the turn. And as it goes along, you can see here that the neighbors have started turning, but not the ones farther away, and that can lead to loss of cohesion and then eventually breakup of the system. So that's the basic challenge. Of course, if you're going very slow, this won't happen because then the information will have propagated before the turn happens. So essentially your maneuvers become slower and so on. So the problem is this loss of cohesion in the orientation. Okay? Now, what causes this loss in formation or orientation information? So this is the basic equations we had from before. And the question becomes, how does a bird in the middle somewhere change its orientation? Okay. So the idea here is that, let's say this is bird I, the ith agent is, the information it has is II. It looks at all its neighbors, J is the neighbors, and it looks at the difference between its orientation and its neighbor's orientation. So that's a difference in orientation. You average that among all your neighbors. Now, what's your neighbor can depend upon the species and so on, but it's basically a neighbors in a certain range, whether it's forward or backwards or sideways, that depends on the species and so on the application. But essentially it's the average deviation of your orientation from your neighbor's orientation. So that's delta I, okay? And so you're essentially taking that average deviation from your neighbors, scaling it with some scaling factor, and then delta t for the next time step. So the new orientation is the old orientation with a change along, it's like a proportional controller with the average deviation from your neighbors as your error in some sense. All right, so I'm just rewriting this equation again back here. And if you take the, the limit, if you had lots of neighbors and, in the, as your delta t becomes small, this equation, you can rewrite it as a partial differential equation, which is essentially the diffusion equation. Here's a gradient, this is delta t, this is with respect to space. And so you get the diffusion equation. Okay. And the d here is basically the dimensions, whether it's 2D or 3D. And the A here is the average distance between the agents. So this looks pretty much like a diffusion equation. And if you look at diffusion equation, if you have something happens at one spot, the information propagates in a diffusion equation with the square root of t. So that's irrespective of what type of diffusion you're looking at, that's a property of the diffusion equation, of how fast information travels over distance. The other property of diffusion is that information will decay. So for example, if the first bird turns around like this is from the papers from 2014, is the idea is that if one of them starts turning, that turn information should decay over distance. Okay, so that leads to loss of potential formation. So obviously this bird that is far away might eventually say, oh no, I'm losing track, so I might want to fly faster, for example. And so this is why this result is so interesting from this paper, is that they look at this actual data and then figure out, not quite, this actual, if you look at the actual birds, there are several differences. First, the decay, there's not much decay in the turn information that's being propagated. It's almost wave-like rather than diffuse, this square root of t kind of thing. And they also found that, sometimes when the birds lose the flock, they'll fly faster and they'll reorient themselves. But those kind of things, but those kind of, that's called neighbor realignment. You realize you're off and you try to come back. But those realignments are much slower than how quickly this information is propagating inside. So the reorientation information is much faster than anything else. So the other things are happening, but those are second order phenomena. And so the question is, why, right? So it makes it interesting. Okay. Now, there are other approaches to try and maintain distances. For example, people try to see, your policy, instead of just looking at this kind of law here, orientation, there could be a repulsion zone, there could be attraction zone. This all complex, much more complex looking theories have been developed over time. You may not be able to see everywhere, so there may be a dead zone and stuff. Essentially, the paper's finding in 2014 was saying that, okay, those kind of realignments can happen, but the reorientation is the most dominant effect. And then the question becomes, how does the reorientation information travel so fast without decay? Okay. All right. So coming back to our equation, this is the realignment law. So suddenly gamma, the scaling factor has an effect, right? You can scale it up, you can tune it up. And if you tune it up, you will get faster information flow, because it becomes a stiffer system. So that's certainly possible. You can, if you look at the swarm as a network, get a topological map of the network at a local time, then you can get a standard looking matrix equation that describes the motion. Aij is the connectivity between the agents, and gamma is slow tuning factor. Okay. So this is converting that into a network model. And if you rearrange all these terms, in a vector form, essentially you get I minus gamma times K. K is the connectivity or the graph Laplacian that tells you which neighbor is connected to which. And this is the information that's coming from what you're trying to do. And this B is not every agent has information about the source and what you're trying to do. It's only one of the agents, in this case will be the leader. So this B is pretty much zeros everywhere except for one of the birds. Okay, so they have a particular structure to it. But you can look at this expression and say, well, we know when this will converge if this matrix P, which is the I minus this gamma times the connectivity matrix, if its eigenvalues are less than 1, we know we'll get convergence, right? So you certainly need this eigenvalues to be less than 1. Okay. So this is a standard stuff. These people have worked on it for a long time. And you can show that, if, for example, if your gamma is sufficiently small, if your network is connected, you can always show that this will converge, and so you'll get consensus. So eventually you will reach the new orientation. All of them will be in the same orientation. But of course, as we talked about, current theories only talk about the eventual, steady state reorientation, not during the transitions. That's important in these things. And there are some properties here, and this is K inverse times B is identity. That's basically saying, and in the steady state, everybody will be oriented in the same direction. But this is an important property that we'll use later. The fact that if I take K and multiply by identity matrix, I'll get B, and I'll use this later on. And this is just a network property that says that if the network is connected and if it's spinned in the right way, you can invert the matrix, and this inverse will give you 1 because you'll get cohesion at the end. Okay. All right, so coming back, the rate of convergence depends on the alignment gain. Obviously, the connectivity, all that makes difference. So certainly a large gamma in general can increase the response, but there's a limit. You cannot increase it too much. Again, these are network properties, but you can find an upper bound beyond which it goes unstable. Okay? And so that's the fastest you can get. Okay. So that's one limit. So although you can yank up the gain, there's a limit to that. And there's obviously other limits, in actual practice, you may get saturation effects. The system can become stiffer. That means your information update needs to be much faster for stability, essentially. There may be other limits from sensing and communication bandwidths that you may get. And so the people have looked at different other limits as well. But essentially, as you can tell, you can't just speed it up too fast. There's a limit to that. Okay. So there are limits on how fast you can converge, but that's reasonable. It's, we expect that. But of course, the current model is also diffusive. And then this also has to have a decay when you're propagating across the network. So this is where things got interesting. And so let me talk about this delayed self-reinforcement method that we're looking at. And this particular part of the talk is from the ASME publication from 2019. And so remember, the basic equation we're working with is that the change in orientation is a scaling factor times the average deviation from your neighbors. So the modification here is you're going to add a beta times the reorientation you did in the previous time step. So to implement something like this, you don't have to get additional information from the network. You're just looking at your own information. How much change did you make in the previous time step? Okay? And you scale it with the beta and you apply it back. So this beta, we call it the update gain on the delayed self-reinforcement, because you only each agent is just reinforcing itself based on the delayed version of its previous value update. Okay, so we can now rewrite this, and then we can bring it back into a matrix form. And it's interesting. There's a similar notion, obviously, and this was also from information theory and gradient-based algorithms for neural networks. They call this as a momentum term. And this is just a version to show that you don't require any extra information from the network. There's a network information is the average deviation from your neighbors. This is just your previous information that you had, and you're just using that. And so a rewriting of the same thing here, nothing new. Again, some more rearrangements, and you're going to take the limit. And now in the limit, this is the partial differential equation you get. Okay, so the beta is the DSR gain that we have here. It pops up in a couple of places. This is the spatial derivatives. And this, interestingly, is called the damped wave equation, or the telegraphic transmission equation. Okay, it's a second order equation. Okay, so that's the second order equation on the top here. And if you put beta equal to 1, this term becomes, here you get a 1, this becomes 0. And you get the exact wave equation. Okay. And then if you put beta equal to 0, you get the diffusion equation. So interestingly, the beta switches you between the diffusion and the wave, and it's somewhere in the middle. Okay. And of course, you could ask how to select the parameter in an optimal manner and the stability conditions for the graphs. So one approach is, if you have a local graph that you put together, you can look at the dominant dynamics and make it critically damped. And so basically that's what I'm doing here. So you look at the network topology. This A is basically the connectivity matrix that we talked about before. You convert in the Jordan form, and then you can get the modal equations, which is second order for the first mode and the second mode and so on. And then you try to choose your beta so that you can get critical damping. Okay, so it's a standard second order equation, and then you can obviously find the beta analytically to find the critical damping for the main mode. And then that's the optimal critical damping to avoid overshoot. And then from that, you can figure out the settling time you get. So this is how fast you transition from one to the other. And you can, this is the settling time with this new method. And this is previous settling time. And what's interesting is you get the square root, which tells you if this is very large, you can get substantial improvements potentially with this approach. And then just similar to previous work, even with this beta, this graph Laplacian and the identity matrix form this Perron matrix, and that determines stability. The same thing happens here. You just get a much more complex looking matrix, but you can still come up with guarantees for stability, and you can find bounds on what betas you can choose to ensure stability. All right. So I'm going to show you some preliminary results on how this worked out. So we'll do two cases. We'll do this random one that we started out in the beginning with and without the new method. And this will be a grid-like structure. So you can actually see how information propagates with distance. We can quantify that. And so remember, this was the video, which is like grid-like structure. And it, oops, let me go back here. So again, this starts rupturing because the agents here haven't changed yet, but the neighbors are starting to change. And based on the math, we said, okay, let's fix an update time here per 0.01 seconds. So then you have a limit on how much gamma you can choose. Okay, and if you choose your gamma to be 100, you get the 2-second settling time is about 96 seconds. So it takes, 69 seconds. It takes 69 seconds for all the agents to go from the initial configuration to the new configuration. And so this is what we're talking about. Typical networks talk about the initial and the final, but not cohesion during the transition. And this gamma is the max you can get. Actually, 101 is unstable. And so this shows the unstable one. And so the maximum gain you can get is about 100. So with that, with the highest gain you can set without the DSR, you get about 69 seconds for settling. Now you add the DSR, so you have an extra parameter you can choose. And you can try to find the beta, which is optimal for settling time numerically. And that turns out to be about 0.96. And the settling time reduces from 69 seconds to about 2 seconds. Okay. And actually, interestingly, the optimal beta from the critical damping is pretty close to the numerical search for this particular application, for this particular example at least. Okay. But interestingly, it captures all the superfluidic-like behavior that you see. So for example, if you have diffusive equations, you get this square root of t propagation of information, and how far the information is propagated with time. Whereas in this other case, you get a flat proportional t kind of thing. So it does get that behavior. And so it matches, what you're expecting from the nature issues. So you can come back and say, well, after all, this was a second order equation, in the limit. Why don't we just discretize this second order equation? Then you'll get second order dynamics. And wouldn't that be the same? Okay. And the answer turns out to be no. If you just discretize this higher order dynamic, the second order dynamics, you'll require a much higher bandwidth for the system to be stable, to give similar performance. And so this is the second order system. So instead of doing a first order system and adding this delayed method, you start with the second order system and you discretize it. Turns out, if you yank up the gain towards a higher value, you can get a fast response as well, but you need to have a bandwidth which is about 100 times faster, higher than 100 times faster sampling than the previous one. And so it is not quite the same as just discretizing a second order equation. And some videos of simulations here. So obviously this is all simulations, so it has this rupture and you start with the same thing with this optimal DSR because it looks like they're marching, it looks pretty interesting. And same thing with this randomized one. and you can get higher performance. So you basically can get tighter turns, faster turn maneuvers, and so on. It leads to this parallel, almost parallel turns that we talked about, agent which is close or far. If you look at their trajectories, they are extremely parallel. And then you can compare things like, what is the peak radial acceleration kind of ideas. Without the DSR, there's a difference between the radial accelerations you're getting. Whereas with this DSR approach, they tend to be much closer to each other, which is what that paper was saying. So to recap over this swarm results that we're talking about, it's a diffusion-like spread. Information propagates square root of t, dampens out about space. With a DSR, you get this wave-like thing back again. Information is proportional to time with smaller decay and increases synchronization. And it is not the same as a second order one. Okay, that's important. It doesn't require additional sensing, doesn't require additional increase in bandwidth, which you might require if you want to go for the higher order model. And it does improve the information transfer through a swarm. So it seems to improve cohesion. Okay. But even if you looked at these results, during the transition, they were not cohesive. So if you look at, if I look at the picture again, sorry, going back in a faster way, this was, this transition, even in these cases, were not cohesive, right? You still have differences between the birds. So you can say you speeded up the system, which was nice, but definitely not, without having to increase your bandwidth, but it's still not cohesive. And of course, it explains some of the results in nature, which is nice too. But with research, you always find one question leads to the other, and the question becomes, can we do better? What is the ideal cohesive approach? Can you get them cohesive during the transitions? Okay, and then if you can find the ideal one, can you implement that in a distributed manner? Can you extend that to high order systems? Because in actual practice, your robots or your vehicles will have higher dynamics, and how do you do that? And so this is the second paper from Automatica from 2020 that goes through this method and actually shows it that this could be done for higher order systems with nonlinear dynamics. So let's come back to this from first principles and ask ourselves, how can you make all the agents cohesive? That means you would like their behaviors to be exactly the same if you could, right? If you could. And so let's take the agent ith agent and assume it's we'll start with first order here, and then later on it can be generalized to higher order nonlinear systems. But if you have a zi dot, so the agent dynamics is first order, you have some alpha, which is your tuning parameter that allows you to achieve settling. And this is a source information. So this is a desired trajectory, right? So if the agent I has information, the desired trajectory is a first order system, it behaves in this manner. So if every agent had the exact same behavior, right? So zi dot is alpha zi, and every one of them had access to the information, desired trajectory. So this is why this becomes identity. So the same source information is going to all the agents. Z is a vector now. And this alpha is the scaling of that vector, then the network will be cohesive, right? Because they're all doing exactly the same thing. And that's the best you can do for like a first order case. And so every agent changes the state in exactly the same manner. Okay. All right, so this is the perfect situation. And now the question is, can we do this in a decentralized manner? And that's the rest of the talk here, for the next few minutes. Because the problem is this is centralized, right? The desired source information has to be accessible to everybody. Now, this, of course, is the ideal case. So if you have this bunch of connected vehicles, if you could tell every vehicle by using a network, or a wireless technology or anything other communication that you're going to make a turn or you're going to speed up, it'll be cohesive. You can go as close as you want to each other because they're all going to behave exactly the same manner. But of course, that's centralized and not decentralized. And so we'd like to see, can we decentralize this thing? Okay. All right. So we're back to our state where this is fully centralized algorithm, where the information is available to every single one. That's why this is identity here. So I'm going to do some manipulation here. I'm going to multiply by k. K is a network the Laplacian, which tells you which agent is connected to which agent. So that matrix, remember, was invertible. And one more property, if you remember, was k times identity is b if the network is connected and so on. And so I'm going to take that k and multiply everything by k. And then I scale it by a beta. We'll figure out how to choose a beta after all later on. But the important thing is K times identity is this B matrix. So this B matrix now becomes the network behavior where only one of the agents might have access to it in a specific application. All right, so we're taking this equation, multiply by this whole thing. I'm going to take this beta K to the other side, add Z dot on both sides. I'm just rearranging this equation. I've not done any approximations yet. It's just the same equation. In this particular format, you should get exact tracking. Okay, and they should all be ideally cohesive. Okay, so I've just rewrote this on the top here. So this is a perfect cohesive equation. They will all behave in exactly the same manner. So they need to be decentralized. I should actually say decentralized, not distributed here. All right. Now, so the ideal cohesive law can be written as a network law, okay, in this case, because now in this case, the information is only going to, let's say, the leader agent, because this B is not like fully one. But in this case, the problem is that the Z dot appears on both sides. So this is still ideal in a network sense, but Z dot appears on both sides. So you can't compute Z dot because you need Z dot to compute Z dot. All right, there were some notions of trying to do this previously. There were some papers that came up, but it couples the whole network. You just can't compute this. So our innovation, one of the innovations is to say, well, let's approximate this Z dot by taking this delayed information idea that we had in the previous paper, taking ZT minus ZT over tau. So it's an approximate derivative. And so you're using your previous information to get the Z dot. And the interesting thing is you only need your own derivatives and previous information from your network. And so if you rewrite this now, you get a delay-based approximation of the right-hand side. And this is implementable. So what we have taken is we have taken this ideal cohesion and implemented it using a delayed version. Okay? This is a decentralized algorithm. And in the limit, this becomes the ideal cohesive equation. Okay? There are other people who have looked at gradients of potential, right? You can think of a network as a gradient of a potential by Richard Murray and Saber. And they also come up with a similar idea saying that if you look at the update loss in a network, this is the same thing like gamma times L, which is a graph Laplacian. So you can do this, they call it, this is the Nestor type approach. You can take that equation, and what we are saying is that idea could be expanded by what people call Nestor's method from optimization theory, which includes a momentum term and an extra term. So this is the most generalized approach that people use for gradient-based searches, which includes momentum term and the Nestor term. And so what we are doing here, so in the Nestor term, we can see there's a K-1 term that appears here. So it has this resemblance to that kind of theory, is what we're getting here. And of course, our tau here, it doesn't have to be just your previous time step. It could be a few steps before that as well. There's also connections to a lot of our community that's working on delayed controls and so on. There's connections with theories for that. And so there's a bunch of things going on, but none of them can do nonlinear systems nor systems with high order dynamics. Even the Nestor's methods are only applicable to first order systems with a single delay. So the question became then, can you do some math here and prove that this is still stable? What are the conditions for stability? And so you can convert this equation into a matrix form where you have a delayed differential equation. And as some of you know, delayed differential equations has a long history, starting from 50s. And a lot of people in our community has also picked up in different applications of this. And from, you can do some work and show that you can guarantee stability under some conditions, and you can come up with these conditions for the network. And the proof of that is in the Automatica paper. And the more interesting thing is that, current methods like Nestor methods for information theory and graph optimization theory is only applicable to first order systems. What we're able to do is take the same dynamics idea and apply that to higher systems with generalized nonlinear dynamics. As long as your relative degree is the same, you can put in the output tracking form, and the output tracking form, you get the standard format, for the dynamics. And then you can still use this same ideas that we had to say what is the ideal cohesive dynamics, and then from that do this approximation of the right-hand side, and then try to come up with proofs for this. I am not going to go through the proof today. It's a little bit delayed, a little bit of a complicated problem, detailed proof, but essentially you can come up with an argument that shows, you can come with a condition that shows that, you can ensure stability. One of the things to note is this is the delay that we are talking about. So you can see if the delay is 0, this term becomes 0. Of course, the right-hand side also becomes small. See, there's a rate at which these two become 0. You can ensure bounds on the, you can ensure that this whole delay-based approach will still be stable. And so this is trying to figure out stability conditions. And the filter selection is also really important. There's the other knob you can turn is this filter about which trajectories you're going to track. And the proof, it's a trade-off between guaranteed stability and tracking bandwidth, essentially. All right. So this is the rationale. Basically, it says that we can now get really cohesive dynamics during the transition for high order systems. And that basically is the novelty of the result, is this applicability to high order systems compared to all the different methods that people have been using in other applications like gradient-based searches. So, results in simulations is pretty easy, but the key point I want you to remember is it's not just whether we get there that's important, but how you get there is also important, okay? And so here's a paper, the results from the Automatica paper. You have this, you're making a transition with this network, and there's differences between the agent responses because it's not cohesive. And this obviously, of course, is simulation, so it gets you perfect cohesion out here. And that's the beauty of it. You're not changing the settling time, right? The response time is pretty much similar, but you get cohesiveness. Now we've been trying to apply that to heterogeneous vehicle applications these days. So Anuj is working on some of these things. And here's an application. We apply this in experiments to a system of robots. Well, that was my alarm to make sure. I'll stop in a couple of minutes. Here, what you're trying to do is a bunch of robots. They're all independent. The first robot on the right has information of the desired trajectory, and they're trying to move this extremely flexible structure. Basically, it's a spring, very weak spring. And so the idea is that, if you're cohesive, they'll all move in exactly the same manner, right? And if you're moving a flexible structure like an uncured composite, that could lead to damage. There's some interesting applications in manufacturing which motivated this thing. But here's a really beautiful experimental results from Joshua. And this is what happens. So the first agent has information, and so it's moving. And then as you go further away, your information hasn't quite propagated yet. And so that's why you get this decay, the change in the information. And obviously that in this application, it leads to large deformation. There's a lot of friction. It's a tough problem. It's amazing that he actually got this to work with all the friction and the problems that he ran into with this thing, which is all not modeled. It's all simple models here. And then this is a cohesive response. And this is the difference. When it's cohesive, you get there's still small deformation, but the deformations are much smaller. Okay. And it's not like it's slowing down to achieve this. That's the other important thing. Okay. And so there's two ways to look at it. For the same amount of deformation, you can go faster, or for the same time, you get much smaller deformation. So either way, whichever is important for the particular application. And that's the cool thing about this problem. All right, let me see. So let me conclude. Okay, so current network models aim to achieve synchronization at the end of a transition. So the steady state is cohesive, but not during the transition. So the network can lose cohesion during transition, which can adversely affect performance in some applications. Of course, in some applications, you might not care. And the DSR enables cohesion during the transition, not just in the final state. So you can basically track trajectories. That's the basic idea. And this is generalizable to systems with high order systems and nonlinear dynamics. The key in this case is to make sure that the relative degrees are the same. In fact, they can be heterogeneous, it doesn't matter. And then the application in autonomous vehicles and multi-agent application is something we're trying to work about. So it's actually very easy to apply. If you look at it, additional effort you have to do, it's actually very little. You're just using your prior information. Of course, you have to tune the gains appropriately. So I think if you're trying anything, it's worth, if you're working on these problems, it's worth a try. So I'll end here. I'm going to have a slide here with two leaders here. And this simulation is kind of fun to look at. So I'll stop here and take your questions. Thank you.